You have experienced this more times than you can count. You pour a fresh cup of hot coffee, steam rising, aroma filling the room. You turn away for just a moment. When you come back, it is already lukewarm. Not cold, but no longer hot. And the strange part is not that it cools down, but how fast it happens at the beginning. Why does coffee seem to lose heat so quickly at first, and then much more slowly later? This simple, everyday mystery hides one of the most profound ideas in physics, an idea Richard Feynman loved to explore, because it shows how the universe behaves in the most ordinary moments of life. Before we go deeper, take a second to think about this question yourself. Have you ever noticed that blowing on coffee helps it cool faster, but covering it keeps it hot? Or that a wide mug cools faster than a tall one? Leave a comment with what you think is really happening here, because by the end of this video, you may see your morning coffee very differently. If you enjoy explanations that turn simple questions into mind-expanding ideas, subscribe to the channel, leave a like, and share your thoughts in the comments. Your interaction helps this content reach more curious minds. Now, let us begin exactly where Richard Feynman would start, with curiosity about something that seems too trivial to matter. Feynman often said that nature does not care whether a problem looks simple or complex. The same laws apply to coffee cooling on your desk and to stars cooling in space. At the moment you pour hot coffee into a cup, there is a huge difference between the temperature of the coffee and the temperature of the surrounding air. This difference is the key. Heat always flows from hotter objects to cooler ones, never the other way around. This is not a preference. It is a rule of the universe. The greater the temperature difference, the stronger the flow of heat. At first, your coffee is much hotter than the air, the table, and the cup itself. Heat rushes out rapidly. Energy escapes into the surrounding air, into the cup, and even into the surface beneath it. This is why the first few minutes feel dramatic. The coffee goes from burning hot to merely warm very quickly. But here is where Feynman's insight becomes important. Cooling is not linear. It does not happen at a constant rate. As the coffee cools, the temperature difference between the coffee and its surroundings becomes smaller. With less difference, the flow of heat slows down. The universe is not trying to make your coffee cold as fast as possible. It is simply equalizing temperatures. This idea is often summarized by what physicists call Newton's law of cooling, but Feynman emphasized something deeper. He explained that laws like this are not commands. They are descriptions of how countless microscopic interactions add up to a predictable pattern. Inside your coffee, billions of molecules are vibrating, colliding, and transferring energy. At the surface of the coffee, fast-moving molecules pass their energy to slower-moving air molecules. Every collision is tiny, but together they drain heat away. Now consider something subtle. The surface of the coffee matters more than most people realize. A wide mug exposes more coffee to the air than a narrow one. More surface means more opportunities for energy to escape. This is why shallow cups cool faster. It is not magic. It is geometry meeting thermodynamics. And then there is evaporation. This is one of Feynman's favorite examples of how invisible processes shape our world. When the hottest molecules at the surface of the coffee escape into the air as vapor, they take extra energy with them. This robs the remaining coffee of heat. When you blow on your coffee, you are not just pushing air around. You are helping those energetic molecules escape faster, accelerating the cooling process. Pause for a moment and think about this. Do you usually blow on your coffee or let it sit? And did you ever imagine that by doing so, you were assisting molecules in their escape from liquid to air? Share in the comments what you do and why you think it works. But here is where the story becomes even more interesting, and where Feynman's way of thinking truly begins to melt your mind. Cooling is not just about coffee. It is about time, probability, and the unstoppable march toward equilibrium. The same principles govern how a planet cools after forming, how your body loses heat on a cold day, and how the universe itself evolves. At this point, the coffee is no longer scorching hot, but it is still warmer than the room. Heat is still flowing outward, just more gently now. The process continues, quiet and inevitable, guided by the same rules that govern everything from atoms to galaxies. And this raises a deeper question that Feynman loved to ask. If the laws are so simple, why does the world feel so rich and complex? Because beneath this simple cup of coffee lies a universe of motion, chance, and energy exchange that never truly stops. And to understand why coffee gets cold so fast, we must now look even deeper into how nature measures change, how time itself sneaks into physics, and why some processes can go forward but never backward. Continue watching, because in the next part, we will follow Feynman's thinking into the heart of heat, randomness, and one of the most misunderstood ideas in all of physics. When Richard Feynman talked about heat, He never treated it as something mystical. For him, heat was motion, pure motion. Every atom in your coffee is vibrating, sliding, and colliding with its neighbors. Temperature is simply a way of measuring how intense that microscopic motion is. Hot coffee means the molecules are moving violently. Cooler air means the molecules move more slowly. Now imagine placing these two worlds next to each other. On one side, fast, energetic coffee molecules. On the other, slower air molecules. When they meet at the surface, collisions happen. Energy is transferred. The fast ones slow down a little. The slow ones speed up a little. This is not a decision made by nature. It is statistics. Over time, energy spreads out because there are far more ways for energy to be evenly distributed than unevenly concentrated. This idea fascinated Feynman because it explains why certain things feel irreversible. You never see a cold cup of coffee spontaneously become hot while the room cools down. Not because it is forbidden, but because it is unimaginably unlikely. The number of molecular arrangements that correspond to hot coffee in a cold room is tiny compared to the number that correspond to warm coffee in a warm room. Here is where many people get confused. They think the laws of physics say coffee must cool, but at the deepest level, the laws allow the opposite. They simply do not favor it. The universe plays dice, as Feynman liked to say, but the odds are overwhelmingly stacked in one direction. Think about this and leave a comment. If the laws technically allow coffee to heat up by itself, why do you think it never happens in real life? As the coffee cools, something else subtle occurs. The rate of cooling slows down. At first, energy pours out rapidly because there are many fast molecules eager to give up energy. Later, when the coffee is only slightly warmer than the room, the difference is small. Collisions still happen, but they exchange much less energy. This is why your coffee seems to reach a stubborn, lukewarm state and stay there for a long time. Feynman loved pointing out that this behavior is not unique to heat. It appears everywhere in nature. Big differences drive fast change. Small differences lead to slow change. This applies to physics, chemistry, economics, and even human behavior. Rapid change slows as balance is approached. Now consider the cup itself. The cup is not just a passive container. It plays an active role in the cooling process. When you pour hot coffee into a cold cup, some heat immediately flows into the cup. The cup warms up. That energy is now spread into more matter. More molecules are sharing the same energy, which lowers the temperature of the coffee faster than if the cup were already warm. This is why preheating a cup keeps coffee hot longer. You are reducing one of the pathways through which energy can escape. Small changes in initial conditions can have noticeable effects, and Feynman emphasized that understanding these details is what separates deep understanding from memorized formulas. There is also radiation, another invisible player. Hot objects emit energy in the form of electromagnetic waves. You cannot see it, but it is happening constantly. The hotter the coffee, the more energy it radiates. This effect is weaker than evaporation or air contact, but it is always present. Even in a vacuum, coffee would eventually cool by radiating energy away. Pause and think about this. If you drank coffee in space, inside a perfectly sealed cup, what do you think would cool it faster, radiation or conduction through the cup? Share your intuition in the comments. What makes Feynman's perspective so powerful is that he never stopped at naming effects. He wanted to know why they must exist. Heat spreads because spreading is overwhelmingly more probable than concentrating. Cooling feels fast at first because probability favors rapid energy transfer when differences are large. Slowing down near equilibrium is not a failure of the process. It is the natural outcome. At this point, your coffee is approaching the temperature of the room. Molecular motion inside it is becoming similar to the motion of the surrounding air. The dramatic part of the cooling is over, but the deeper lesson is just beginning. Because hidden inside this everyday experience is one of the most important ideas in all of science, the arrow of time. Why does time seem to move forward when coffee cools, but never backward? Why do we remember the past and not the future? And how did Feynman use simple examples like this to explain concepts that reach all the way to the origin of the universe? These questions are not philosophical distractions. They are embedded in the physics of your coffee cup. And to truly understand why coffee gets cold so fast, we must now follow the trail from heat to time itself, exactly the way Feynman did. When Richard Feynman spoke about the arrow of time, he often returned to examples that felt almost too simple. A cup of coffee cooling on a table, cream mixing into liquid, smoke dispersing into the air. These processes all move in one direction, never the other. And yet, at the microscopic level, the basic laws of physics do not care about past or future. They work the same forward and backward. So where does this one-way feeling come from? To understand this, imagine freezing time at the exact moment your coffee is still hot. If you could see every molecule, you would notice something remarkable. The energy is unevenly packed. Many fast-moving molecules are clustered together in one place. This is a highly ordered situation, even if it looks ordinary to us. Now, let time run. Molecules collide. Energy spreads. Order fades into disorder. This spreading is not driven by a rule that says disorder must increase. It happens because there are vastly more disordered arrangements than ordered ones. Feynman loved emphasizing this point. Nature does not push systems toward disorder. Statistics do. This is what physicists call entropy, a word that sounds intimidating but hides a simple idea. Entropy measures how many different microscopic arrangements correspond to what we see macroscopically. Hot coffee in a cold room has low entropy because there are relatively few ways to arrange molecules so that energy is concentrated in one small region. Warm coffee in a warm room has high entropy because energy is spread out in many possible ways. The coffee cools quickly at first because it is racing downhill toward a state with many more possible arrangements. Once it gets close, the slope flattens. There is no longer a strong statistical push, so change slows. Here is something to think about. If entropy explains why coffee cools, do you think it also explains why memories work the way they do? Why we remember yesterday but not tomorrow? Leave a comment with your intuition, because the connection is deeper than it seems. Feynman argued that our sense of time flowing forward is tied to entropy increase. We remember the past because the past had lower entropy. The present and future have higher entropy. The cooling of coffee is not just about heat. It is about why the universe has a direction. Now let us return to the cup itself. Even after the coffee has nearly reached room temperature, microscopic motion never stops. Molecules continue colliding forever. What changes is not motion itself, but imbalance. Early on, imbalance is strong, so effects are dramatic. Later, balance dominates, and change becomes subtle. This leads to a fascinating question. Why does coffee feel like it cools faster than it heats up? If you place a cold cup of coffee in a warm room, it warms slowly, but hot coffee cools quickly. The reason again lies in probability. When energy differences are large, there are many efficient pathways for transfer. When differences are small, most collisions cancel out statistically. Feynman often pointed out that people mistakenly imagine heat as a substance flowing out. But heat is not a thing. It is a process. It is the transfer of energy through motion. And processes depend on differences. Big differences produce strong effects. Small differences fade into noise. Another detail that sparks curiosity is stirring. When you stir coffee, it cools faster. Why? Because you are constantly bringing hotter liquid from inside the cup to the surface, where energy can escape more easily. Without stirring, the surface cools first, forming a slightly cooler layer that slows further heat loss. Stirring destroys this layer and restores imbalance. Think about how many everyday actions unknowingly manipulate entropy. Stirring, blowing, covering, choosing a cup shape. Each one subtly changes how energy spreads. And this is exactly what Feynman meant when he said understanding physics gives you a new way of seeing ordinary life. At this stage, the coffee has almost reached equilibrium with the room. It feels boring now. Nothing dramatic is happening. But in reality, something profound has occurred. A highly ordered situation has transformed into a far more probable one. Energy has dispersed. Information about the initial state has been lost, and time has unmistakably moved forward. Yet there is one final twist. Even equilibrium is not perfect stillness. On microscopic scales, tiny fluctuations never disappear. Molecules constantly jiggle. Energy briefly concentrates and disperses again. These fluctuations are usually too small to notice, but they remind us that the universe is never truly at rest. This brings us to one of the most mind-bending questions Feynman raised. If entropy always increases, how did the universe ever start in such a low entropy state to begin with? Why was there ever hot coffee in a cold room at all, on a cosmic scale? To answer that, we must step far beyond the coffee cup and look at the universe itself, its beginning, and the strange conditions that made everything we see possible. Richard Feynman often reminded his students that the most important questions in physics do not live in equations alone. They live in why the universe started the way it did. When we talk about coffee cooling, we are really talking about a universe that began in a remarkably special state. A state where energy was unevenly distributed, where differences existed, and where change could happen. Imagine for a moment a universe that began already in perfect equilibrium. No hot regions, no cold regions, no gradients at all. In such a universe, nothing interesting would ever occur. No stars would form. No chemistry would arise. No life would exist. Coffee would never get cold. because it would never be hot to begin with. The reason your coffee cools so fast is ultimately tied to the fact that the universe allows differences. Feynman emphasized that physics is not just about motion, but about the conditions that allow motion to matter. The early universe was smooth in some ways, but incredibly low in entropy in others. That imbalance made everything else possible. As the universe expanded, energy spread out, structures formed, stars ignited, planets cooled. Every one of these processes follows the same logic as your coffee cup. Big differences first, rapid change. Smaller differences later, slower change. The pattern repeats at every scale. Now think about your coffee again. When it is first poured, it contains a lot of useful energy. You can warm your hands on it. You can feel the heat on your skin. As it cools, that usefulness disappears. The energy is still there, but it is spread out into the room. This idea, known as the degradation of energy, fascinated Feynman because it explains why not all energy is equally valuable. This is another subtle point that sparks debate. Energy is conserved, always, but the ability to use that energy is not. High-temperature differences allow work to be done. Low-temperature differences do not. That is why your coffee cannot reheat itself using the warmth of the room. The energy is too evenly spread. Consider this question and share your thoughts. If energy is never destroyed, why do we so often feel like it is being wasted? Feynman used examples like this to challenge the way people think about efficiency, machines, and even life itself. Living organisms survive by feeding on differences. Differences in temperature, chemical concentration, and energy availability. When differences vanish, life cannot function. Another fascinating detail is insulation. When you put a lid on your coffee, it stays hot longer, not because heat stops trying to escape, but because you block the most efficient escape routes. Evaporation is reduced. Air movement is limited. The slope toward equilibrium becomes gentler. This mirrors something much larger. The universe itself has limits on how fast energy can spread. Expansion, gravity, and the speed of light all act like cosmic insulation, shaping how quickly entropy increases. Even the universe cannot rush too fast toward equilibrium, or it would burn through all structure instantly. At this point, the coffee is almost perfectly matched with the room. There is no longer a noticeable flow of heat. But this does not mean the story is over. What remains is the lesson. The reason coffee gets cold so fast is not because it wants to. It is because the universe is built to erase differences. Feynman believed that understanding this changes how you see everything. Your body cooling after exercise, ice melting in a glass, even the way ideas spread through society, all follow similar patterns. Rapid change when differences are large, slow settling when balance approaches. And now we arrive at the final, mind-bending question. If entropy always increases, and if equilibrium is inevitable, what does this say about the future of the universe? Will everything eventually reach the same dull temperature, the same lifeless balance? This question, known as the heat death of the universe, is not science fiction. It is a direct extension of the same physics that cools your coffee. And to truly grasp what Feynman uncovered, we must now look forward, far beyond the cup on your table, into the ultimate fate of everything. If Richard Feynman were holding that cup of coffee in his hands, this is where he would smile and pause. Because from something so ordinary, we have arrived at one of the most profound ideas ever discovered. The same reason your coffee gets cold so fast may also describe the distant future of the universe itself. As time goes on, differences fade, stars burn their fuel, galaxies drift apart, energy spreads thinner and thinner across space. Eventually, if nothing intervenes, the universe approaches a state where no significant temperature differences remain, no gradients to drive motion, no imbalance to power change. This is what physicists call thermal equilibrium on a cosmic scale. In such a future, nothing dramatic happens, not because laws have stopped working, but because they have finished their work. Just as your coffee reaches room temperature and becomes unremarkable, the universe may one day reach a state where everything is equally unremarkable. This idea unsettled many people, but Feynman treated it with clarity rather than fear. He reminded us that physics does not judge outcomes as good or bad. It describes what happens and why. And the reason everything slows, cools, and fades is the same reason your coffee does. Probability overwhelmingly favors spread over concentration. Yet there is a subtle comfort hidden here. The fact that coffee gets cold quickly tells us something extraordinary. It tells us we live in a universe that is not yet finished. A universe still full of differences. A universe where stars still shine, where life can exist, where change still matters. Every warm cup of coffee is a reminder that equilibrium has not yet been reached. There is still free energy available, still structure, still time flowing in a meaningful direction. Feynman often emphasized that understanding this does not make life less magical, it makes it more so. To realize that the same laws govern your morning routine and the fate of galaxies is not depressing, it is awe-inspiring. And there is one final twist that truly melts the mind. On the smallest scales, the future is not fixed. Quantum mechanics introduces uncertainty. Tiny fluctuations can be amplified. New structures can emerge as long as differences exist. The universe is not a rigid machine winding down in silence. It is a dynamic system exploring possibilities, guided by probabilities. Your coffee cools because there are vastly more ways for it to be cool than hot. But the fact that it was hot at all means the universe once arranged itself in a very special way. That special beginning is what allows curiosity, consciousness, and questions like this one to exist. So the next time you notice your coffee losing heat faster than you expected, pause. You are not just watching a beverage cool. You are witnessing the arrow of time in action. You are seeing entropy increase. You are seeing the universe gently but relentlessly smoothing itself out. And yet, here you are, observing it, thinking about it, commenting on it. That alone is remarkable. If this explanation changed the way you see something as simple as a cup of coffee, leave a comment sharing what surprised you most. Do you see entropy differently now? Do you feel time differently? Conversations like these are how ideas stay alive. Feynman believed that the pleasure of finding things out was one of the greatest joys a human could experience. And sometimes, all it takes to begin that journey is a simple question, asked at the right moment, over a cup of coffee that is getting cold just a little too fast.